It was a December night in 2018 when a wave tore out of the complete darkness along the coasts of Java and Sumatra, killing more than 400 people without a single second of earthquake warning. It didn't come from a fault slip or a mega thrust break. It came from a solitary island volcano known as Anak Krakatau. In a single frantic 10-hour window on July 8th, that exact same peak erupted 6 separate times, sending Indonesia's volcanology agency scrambling to raise its official warning to the second highest level on the entire scale. The immediate concern now is whether that silent, lethal water column is being reloaded. Over a single stretch of less than 10 hours, the volcano known as Anak Krakatau fired off 6 distinct eruptive pulses from a crater sitting squarely in the middle of one of the most densely populated maritime choke points on Earth. The first blast struck just 11 minutes past midnight local time. While the dark hid the emerging ash column, the seismic network registered a continuous maximum amplitude of 24 millimeters, lasting roughly 40 seconds. As daylight broke, 5 additional blasts stacked directly on top of one another, with the final burst logged just before 10 a.m. This is the same peak that only 2 weeks prior was merely breathing out a pale, gray-white steam plume roughly 100 meters above the vent, held at a modest alert level with a 2-kilometer marine exclusion zone. The story then was simply that a volcano had woken up. The story today is the direction and velocity at which it is accelerating. In 14 days, every critical parameter has trended in the wrong direction. The alert level stepped up, the exclusion perimeter widened, the eruptive bursts transformed from isolated puffs into tightly clustered salvos, and the ash column darkened from white steam to pitch black. What we are observing is not a single isolated spectacle, but a real-time escalation at a marine edifice that has already proven its ability to kill hundreds without a whisper of seismic warning. To sharpen the headline framing, this is not an impending subduction megathrust earthquake, nor is it a repeat of the planetary-scale 1883 VEI-6 caldera collapse that famously altered global atmospheric temperatures. The true hazard here is far more specific, physical, and localized: a volcanically generated flank collapse tsunami. The accurate mechanism is actually the far more terrifying story. When an unstable, rapidly rebuilding island cone standing in deep water collapses, millions of tons of rock displace the sea in seconds, generating a high-velocity tsunami that hits adjacent shorelines before any regional warning system can even process the event. That specific structural instability is the core mechanism this episode will track. To understand why this precise threat commands global scientific attention, we have to look at the continental architecture of marine hazards. Across North America, we watch similar structural systems with intense monitoring networks. While North Americans look to the Cascadia subduction zone off Vancouver Island, silent since the magnitude 9 megathrust of January 26, 1700, or the Queen Charlotte Fault off Haida Gwaii, which generated a massive magnitude 8.1 quake in 1949, marine volcanic structures represent an entirely different physics problem. The danger isn't just the shaking, it is the physical mass displacement of water by failing rock. On July 2nd, the Center for Volcanology and Geological Hazard Mitigation raised Anak Krakatau to Alert Level 3, known as Siaga. That sits precisely one rung below AWAS, the absolute maximum warning. This wasn't an automated administrative update. Every step up on a volcanic hazard matrix carries immediate, severe economic consequences, closing lucrative commercial fishing grounds, vital ferry lanes, and regional shipping corridors. Along with the designation, authorities expanded the marine exclusion zone out to 3 kilometers in every direction. The official agency bulletins flagged 4 specific hazards in plain terms: pyroclastic flows, incandescent lava, thrown ballistic blocks, and heavy ash deposition. But the primary driver behind the decision lies deeper in the real-time geophysical telemetry. You read a marine volcano's state using 2 primary diagnostic tools: ash colorimetry and subterranean seismic amplitude. The color sequence over those 10 hours shifted rapidly from white through gray to dark black. White indicates harmless meteoric steam. Gray signals that country rock is being pulverized. Black denotes dense, fresh, juvenile magma being violently torn apart and blasted skyward at temperatures exceeding 1,000 degrees Celsius. The ash plumes climbed to 250 meters above the summit, but the internal seismic signatures told an even more intense story. Across those 6 pulses, the seismic amplitude continually surged, moving from 24 millimeters up to 44.4 millimeters, nearly double the initial strength. Crucially, the system never went quiet between events. Monitoring stations recorded continuous volcanic tremor, the unmistakable rhythmic hum of pressurized magma, gas, and superheated fluids forcing their way through the mountain's internal conduits. The daily tally recorded continuous low-frequency events, harmonic tremor, and dozens of hybrid multi-phase earthquakes. Hybrid events represent the simultaneous cracking of solid basaltic rock combined with fluid transport. The mountain was actively carving out new plumbing under immense internal pressure. A common point of confusion arises when comparing ground observations with satellite data. Local observers recorded modest visual plumes rising 250 meters above the crater, while the Darwin Volcanic Ash Advisory Center, utilizing the Himawari 9 geostationary satellite, tracked dispersed ash clouds at flight level 050, approximately 15,000 feet or 4,600 meters in altitude. This is not a data error or conflicting reports. Ground observers measure the immediate convective column directly over the vent, whereas satellite sensors trace the light, high-altitude ash fraction as it detaches, expands, and drifts southwest across international air routes. Both observations confirm the same reality. The volcano is actively, continuously discharging material into the atmosphere. What makes Anak Krakatau, literally the child of Krakatoa, singularly dangerous is its physical geometry. It is not a mountain on an island. The island itself is nothing more than a loosely consolidated, steep-sided cone of eruptive debris rising directly out of the deep ocean bed inside the drowned caldera formed during the catastrophic 1883 eruption. Sitting in the Sunda Strait between Java and Sumatra, it straddles one of the most heavily navigated marine conduits on the planet. Deep beneath the seabed, the Indo-Australian plate is sliding relentlessly northward, subducting beneath the Sunda plate along the Sunda Trench at roughly 6 centimeters per year, about the rate a human fingernail grows. This relentless tectonic conveyor belt generates superheated fluids that melt the overriding mantle, feeding an arc of lethal volcanism across the Indonesian archipelago. When a landlocked volcano like Mount Meager in British Columbia experiences activity or massive landslides, such as its historic 2010 collapse, the largest recorded in Canadian history, it creates localized river blockages and debris flows. But when a steep, poorly consolidated marine cone undergoes violent internal pressurization, the entire structural flank can give way straight into deep ocean water. That brings us to the nightmare scenario. The danger is a step-by-step physical chain reaction. Continuous explosive eruptions load millions of tons of heavy, unconsolidated ash and lava onto an already dangerously steepened cone. The combination of intense internal volcanic tremor, steam-driven pore pressure, and continuous structural loading triggers a catastrophic structural failure of the southwestern flank. Millions of cubic meters of rock slide into the Sunda Strait in a matter of seconds, displacing an equivalent volume of seawater and driving a massive, unheralded tsunami toward densely populated coastlines. This exact physical mechanism was brutally demonstrated on December 22, 2018. During an ongoing eruptive sequence, roughly 0.2 cubic kilometers of Anak Krakatau's southwestern flank suddenly failed, sliding into the ocean. Because there was no massive tectonic earthquake to trigger regional automated sensors, no alerts were dispatched. The resulting wave reached run-up heights of 13 meters, over 40 feet, slamming into coastal resorts and fishing villages at night. At least 437 people died, thousands were injured, and tens of thousands were left homeless. It stands as the deadliest volcanically induced tsunami of the 21st century. proving that this precise failure mode is not a theoretical model, but a recurring physical reality. While the historical 1883 event destroyed 70% of the original island and generated global climate cooling, today's rebuilding cone is significantly smaller and less massive, which reduces the immediate volume available for a single mega collapse. Nevertheless, because the modern cone is built of loose, newly erupted material, its structural threshold for failure remains exceptionally low. As monitoring agencies keep their instruments pinned on this active system, 3 concrete checkable signals will determine which direction this crisis turns. First, whether the official status escalates from level 3 to level 4, AWAS, driven by continuous black ash production and ground inflation. Second, whether tilt meters and satellite radar detect measurable slope deformation on the vulnerable southwestern flank. And third, whether the eruptive sequence maintains its current high-density clustering or begins to dissipate. Until those real-time instruments show a clear drop in harmonic tremor and slope strain, the volcano remains fully loaded, highly pressurized, and structurally unstable. The critical question the entire global monitoring network is now trying to answer is whether the steep cone can sustain this rapid accumulation of fresh rock without losing its balance once again. On the morning of May 18, 1980, thousands of observers stood on ridgelines dozens of kilometers away from Mount St. Helens, watching a mountain they believed was merely venting steam. Minutes later, a hidden cryptodome forced a massive sector collapse, triggering the largest catastrophic landslide in recorded human history, and leaving 57 people dead. The warning signs were not absent. They were simply misread because the system was operating outside its known historical baseline. Across the global geological record, from the Garibaldi volcanic belt in British Columbia to the violent subduction arcs of the Pacific Ring of Fire, the baseline is what keeps civil protection agencies from issuing false panics. When a volcano breaches its baseline, every established engineering model and emergency evacuation protocol must be rewritten overnight. To understand why the current behavior at Anak Krakatau has triggered high-level hazard protocols, we have to establish the exact historical baseline of the Sunda Strait system. The headline narrative often frames this active peak as an unpredictable mythical force that erupts without warning or precedent. The real story is far more revealing. This system is a hyper-quantified historical laboratory whose past behavior provides an exact physical roadmap for its current instability. The precise baseline begins on August 26th and 27th, 1883. For centuries prior, the original island of Krakatoa had sat relatively quiet in the Sunda Strait, an unpopulated landmass roughly 9 kilometers long and 5 kilometers wide, dominated by 3 volcanic peaks, Purbawatan, Danan, and Rakata. In May 1883, isolated steam explosions began, but because the island had been dormant since 1680, local authorities treated the activity as a minor geological novelty. That baseline was shattered on August 27th at 10:02 a.m. local time, when a catastrophic VEI-6 explosion destroyed more than 70% of the original landmass. The blast ejected an estimated 25 cubic kilometers of rock, ash, and pumice into the upper atmosphere. The energy release was equivalent to 200 megatons of TNT, more than 4,000 times the yield of the bomb dropped on Hiroshima. The primary noise was registered at a distance of 4,800 kilometers across the Indian Ocean on Rodriguez Island, while barographs tracked atmospheric shock waves circling the globe 7 times. The collapse of the original cone into its underlying magma chamber created a submarine caldera 250 meters deep. That collapse generated a series of displacement tsunamis with localized run-up heights exceeding 40 meters, equivalent to a 14-story building, wiping out 165 coastal villages and killing officially 36,417 people across Java and Sumatra. For 44 years following the 1883 cataclysm, the drowned caldera remained entirely beneath the sea, quiet and submerged. That baseline changed permanently on December 29, 1927. Fishermen operating in the Sunda Strait observed continuous columns of steam and dark ash breaking the ocean surface directly above the center of the 1883 submerged caldera. Magma, forcing its way upward through the sea floor, had begun building a brand new subaerial volcanic cone. By January 1930, the new island had permanently risen above sea level, earning the name Anak Krakatau, or Child of Krakatoa. Over the next 9 decades, scientists established a steady, measurable growth baseline for the young peak. Between 1930 and 2018, Anak Krakatau grew at an average rate of roughly 4.7 meters per year. It was built through a continuous succession of mild strombolian eruptions, short basaltic bursts of lava, scoria, and ash that stacked loosely on top of the steep undersea walls of the 1883 caldera. By early December 2018, the peak had reached an elevation of 338 meters above sea level, containing a total structural volume of roughly 0.3 cubic kilometers. It was a steep, top-heavy cone sitting directly on the edge of a deep underwater drop-off. The baseline assumption among global volcanologists was that Anak Krakatau would continue this slow, steady construction for centuries before generating a major flank failure. That assumption proved critically flawed on December 22, 2018. The volcano did not require a VEI-6 catastrophic explosion to trigger a disaster. At 8:55 p.m. local time, during a period of moderate eruptive activity, an estimated 0.1 cubic kilometers, roughly 64% of the island's total above-water volume, instantly failed along an unstable structural joint on its southwestern flank. Millions of tons of saturated volcanic debris slid into the deep caldera waters. The rapid underwater landslide displaced millions of tons of seawater in under 2 minutes. Because the seismic signal of a landslide is low frequency and lacks the sharp P-wave onset of a tectonic earthquake, automated seismic networks did not issue a regional alarm. 43 minutes later, a series of tsunami waves between 5 and 13 meters high struck the coastlines of Banten Province and Lampung, killing 437 people and injuring over 14,000. The entire elevation of Anak Krakatau was instantly reduced from 338 meters down to just 110 meters above sea level. This is the precise baseline against which current observations are measured. When Canadian researchers at the Geological Survey of Canada monitor complex marine hazards, whether tracking massive submarine landslides off the Fraser River Delta or surveying stability along the Queen Charlotte Fault, they look for structural acceleration beyond established historic norms. The 2018 collapse fundamentally altered the physical geometry of Anak Krakatau. Before 2018, the volcano was a tall, top-heavy tower resting on a submerged crater edge. Today, it is a truncated, rapidly rebuilding cone composed of loose, uncemented tephra, ash, and fresh lava flows, attempting to reconstruct itself on top of a fresh underwater scar. To gauge where this system goes next, monitoring teams are tracking 3 precise baseline metrics. First, the volumetric construction rate. Whether the island is rebuilding its slope angle past the critical 30-degree threshold of physical instability. Second, the composition of the eruptive products, specifically whether magma is shifting from gas-rich basaltic fluid to highly explosive viscous dacite. And third, the depth and origin of the internal seismic tremor network. Until real-time deformation sensors indicate that the new cone has stabilized its foundation, the system remains outside its historical safety margin, operating on a fragile, newly formed structural trigger. A single number flickering on a monitoring screen at a remote seismic station, 44.4 millimeters of continuous peak-to-peak amplitude, tells the entire story of the breaking point. It was recorded at 7:10 a.m. local time on July 8th, nearly double the baseline vibration registered just 7 hours earlier. In geophysical monitoring, an amplitude jump of that velocity is not an incremental shift. It is the exact physical signature of a subsurface conduit tearing open under extreme hydro-magmatic pressure. To understand the physical catalyst behind this escalation, we must step past popular sensationalism and analyze the exact thermodynamic mechanism occurring inside the mountain. The public often imagines a volcanic eruption as a simple balloon popping under pressure. The reality at an island volcano like Anak Krakatau is far more complex and dangerous. It is a phreatomagmatic pressure cooker. When magma at 1,100 degrees Celsius ascends rapidly through shallow crustal conduits, it encounters seawater saturating the porous volcanic edifice. When superheated juvenile magma makes direct contact with cold seawater, the water does not merely boil, it undergoes instantaneous thermal expansion, expanding in volume by more than 1,600 times in milliseconds. This violent steam expansion shatters the surrounding magma into microscopic glass-sharp shards of black ash, driving the eruptive plumes high into the atmosphere and generating high-frequency shock waves through the surrounding sea. The breaking point in the current sequence is defined by how this shallow plumbing system is behaving under sustained stress. Traditional forecasting models relied heavily on distinct, isolated earthquake signals, sharp P-wave and S-wave arrivals that indicate discrete fault slipping. But the telemetry captured on July 8 by the Indonesian Center for Volcanology and Geological Hazard Mitigation revealed a completely different phenomenon: continuous harmonic tremor interspersed with hybrid multi-phase seismic events. Harmonic tremor occurs when a continuous stream of pressurized gas and fluid sets the walls of a volcanic conduit into sustained resonance, much like compressed air forcing its way through a pipe. Hybrid events record the simultaneous fracture of solid rock immediately followed by high-pressure fluid flow. When these signals stack without pause, it proves that the shallow conduit is no longer cooling or sealing between blasts. It is operating as a continuously open, pressurized feed line straight from the deeper reservoir. This thermal and mechanical loading creates a profound structural paradox. As fresh magma reaches the surface, it deposits layers of heavy, hot basaltic scoria and lava directly onto the upper slopes of the cone. But because the island was hollowed out by the 2018 flank collapse, this fresh material is being stacked onto an unreinforced, highly steepened shelf resting on the ocean floor. The angle of repose, the maximum steepness at which loose rock can remain stable without sliding, is roughly 30 to 35 degrees. Aerial mapping and synthetic aperture radar feeds show that parts of the newly constructed summit cone are pushing past 38 degrees. The mountain is literally building itself into a state of structural self-destruction. To contextualize the physical scale for North American viewers, a flank failure of 0.1 cubic kilometers, the volume that slid into the sea in 2018, is equivalent to sliding 40,000 Olympic-sized swimming pools of solid rock into the water in under 60 seconds. If a similar volume of rock were to suddenly detach from the steep subaqueous slopes of Howe Sound in British Columbia, or along the inner passages of the coastal mountains, the displaced water column would race toward coastal shorelines at speeds exceeding 100 kilometers per hour, hitting nearby communities with zero seismic forewarning. The physical evidence confirming this systemic transition comes directly from multispectral satellite imagery and seafloor acoustics. Instruments aboard the Himawari 9 satellite tracked the resulting atmospheric plume expanding southwest across the Sunda Strait, while regional oceanographic sensors detected low-frequency acoustic waves traveling through the marine water column. The consensus among oceanographers and geophysicists is clear. The shallow magmatic system has breached its post-2018 equilibrium. The old empirical models that treated Anak Krakatau as a quiet, predictably growing island no longer apply. The catalyst has been pulled, and the system is actively testing the physical strength of its own freshly built foundation. To monitor which way this physical catalyst resolves, researchers are monitoring three distinct real-time indicators. First, whether satellite interferometry reveals localized ground tilt or surface inflation on the remaining southwestern headwall scar. Second, whether the ratio of SO2 gas emissions spikes dramatically, indicating fresh mantle-derived magma forcing its way to the surface. And third, whether the continuous harmonic tremor transitions into intense, sustained microseismicity across the submarine flanks. Until those sensors show a return to stable baseline levels, the physical plumbing of the mountain remains at its absolute breaking point. At 9:30 p.m. on a quiet Saturday, thousands of people sat in seaside restaurants along the beaches of Anyer and Kurita, completely unaware that a wall of ocean water was already racing toward them in total darkness. There was no ground tremor, no blaring siren, and no warning on any mobile device. Less than 20 minutes later, a 13-meter wave wiped out entire beachfront towns, destroying over 400 lives in a single stroke. That night demonstrated the real-world impact when a volcanic hazard bypasses every conventional alert framework. What begins as microscopic fractures inside a mountain quickly cascades into immediate disruptive reality for real-world infrastructure, transportation, and daily human routines. To translate this mechanism into tangible local consequences, a marine volcano escalating to alert level 3 does not just create a visual hazard for geologists, it immediately reshapes regional supply chains, maritime navigation, and public safety networks. Sensational headlines often frame these events as isolated natural wonders. The direct reality is far more severe. An escalating volcanic cone sitting in a narrow marine corridor operates as an economic and logistical tax on the entire surrounding region. The moment the Center for Volcanology and Geological Hazard Mitigation expanded the exclusion zone to 3 kilometers, it severed vital local fishing routes and disrupted commercial shipping corridors. The Sunda Strait is not an isolated expanse of water. It is a critical maritime transit zone, connecting the Indian Ocean to the Java Sea, carrying tens of thousands of cargo vessels, fuel tankers, and regional passenger ferries every single year. The risk is directly comparable to the supply chain vulnerabilities we track in North America. When the November 2021 atmospheric river struck British Columbia, dropping historic rainfall over 48 hours, it triggered catastrophic debris flows that severed every single rail line and major highway connecting the Port of Vancouver to the rest of Canada. Within days, supply chains stalled nationwide, demonstrating how a single localized geographic bottleneck can disrupt the economic baseline of an entire country. In the Sunda Strait, the persistent threat of volcanic ash and tsunami hazards forces commercial container ships to alter their transit routes, adding hundreds of extra nautical miles, burning thousands of additional liters of marine fuel, and driving up insurance premiums across global maritime trade routes. On the ground, the impact alters daily life down to the minute. Along the coastal communities of Banten Province on Java and Lampung Province on Sumatra, living under Alert Level 3 means continuous operational disruption. When the Darwin Volcanic Ash Advisory Center logged ash plumes climbing toward flight level 050, around 4,600 meters, aviation authorities were forced to adjust flight paths across regional airspace. Modern jet engines ingest volcanic ash, where the extreme heat of the combustion chamber melts the microscopic glass particles, coating turbine blades in liquid glass and causing total engine failure in mid-air. Airline rerouting creates compounding delays that ripple across international air hubs, grounding passenger flights and delaying air freight cargo worth millions of dollars. For coastal towns like Labuan and Rajabasa, the continuous volcanic tremor translates into constant public anxiety and practical disruption. Emergency management agencies have had to install specialized oceanic pressure sensors and coastal radar systems, attempting to build an early warning network where traditional seismic triggers fail. Local fishermen who rely on shallow coastal waters for their daily livelihood find their traditional fishing grounds completely blockaded within the 3-kilometer safety radius, threatening local food security and rural economies. Public safety warnings that usually arrive via automated cellular networks, equivalent to Public Safety Canada utilizing the National Alert Ready system during extreme weather or emergency events, must be completely recalibrated. Because a flank collapse tsunami generates no felt earthquake, emergency planners cannot rely on natural ground shaking as a prompt for evacuation. Instead, communities must rely on real-time acoustic sensors and automated tide gauges anchored offshore. The scale of this risk becomes crystal clear when measured against familiar infrastructure. A wave run-up of 13 meters, the height of the 2018 tsunami, is tall enough to completely submerge a 4-story apartment building or overtop regional coastal seawalls. A structural collapse of 0.1 cubic kilometers represents a mass of rock weighing over 250 million tons, plunging into the ocean in under 120 seconds. If a marine mass displacement of that scale occurred in the Strait of Georgia off Vancouver Island, the resulting displacement wave would strike low-lying coastal municipalities within 15 to 20 minutes, giving emergency agencies virtually zero time to issue public warnings or execute mass evacuations. To track how this real-world escalation unfolds, emergency agencies and logistics operators are monitoring 3 precise metrics. First, whether regional civil aviation authorities issue expanded volcanic ash advisories, forcing broader airspace closures over major international corridors. Second, whether provincial emergency management agencies initiate mandatory evacuations for coastal communities within low-lying inundation zones. And third, whether offshore tide gauges register anomalous high-frequency water level fluctuations. Until these operational indicators return to baseline, the entire Sunda Strait region remains on high alert, navigating the real-world economic and human costs of a volcano that refuses to settle down. 3 distinct seismic sensors spanning hundreds of kilometers across the Sunda Strait, located at Pasaran, Kalianda, and Sabesi Island, all registered the exact same anomalous low-frequency signal simultaneously at 7:10 a.m. on July 8th. It was not 3 separate local microquakes. It was 3 independent readings of a single, deeply pressurized magmatic pulse inside Anak Krakatau. That precise convergence brings us to the ultimate synthesis of this crisis, drawing the absolute, honest line between what science has firmly established and what remains genuinely unresolved. To sharpen the final diagnosis, what we are watching at Anak Krakatau is not a sensationalist media hyperbole, nor is it an imminent global climate-altering explosion like the parent eruption of 1883. What is firmly established by real-time instrumentation is that the shallow magmatic plumbing system is fully energized, actively loading fresh basaltic rock onto a steep, poorly consolidated island structure and maintaining a level 3 hazard posture. What remains unresolved, and what no monitoring agency on Earth can predict with absolute certainty, is the exact structural tipping point of the remaining southwestern headwall scar. Sensors can track the ash height, measure the harmonic tremor, and chart the gas flux. But calculating the precise internal shear strength of an ocean-bound cone undergoing continuous pressurization sits at the very edge of modern geophysical science. When monitoring organizations like Natural Resources Canada or the Geological Survey of Canada assess complex marine hazards along our own Pacific margin, such as the subsea structural stability along the Cascadia subduction zone, or the landslide-prone fjords of coastal British Columbia, they face this same fundamental limit. We can map the fault lines and measure the accumulation of strain, but the exact moment an unstable mass gives way under hydrostatic pressure remains fundamentally unknowable until the failure begins. At Anak Krakatau, the volcano is currently attempting to rebuild its physical summit above an underwater crater scar that collapsed less than 8 years ago. The structural geometry is inherently compromised, but whether the current eruptive sequence will quietly vent that internal pressure through minor ash emissions or culminate in another sudden flank failure is the core question hanging over the Sunda Strait. To know which path this crisis takes, watch for 3 specific, checkable developments in the coming days. First, whether the Indonesian Center for Volcanology and Geological Hazard Mitigation issues a formal elevation to Alert Level 4, AWAS, which would indicate that internal magmatic pressure and ground deformation have reached critical, imminent eruption levels. Second, whether regional bathymetric and satellite radar surveys detect active slumping or rapid structural displacement along the southwestern sector of the cone. And third, whether the continuous harmonic tremor collapses back into low-amplitude sporadic background seismicity. Until one of those three definitive events occurs, the situation remains a persistent, high-risk volcanic escalation contained within an active marine exclusion zone. The true danger of Anak Krakatau has never been the thunderous noise of its ash columns, but the silent, unheralded wave generated when the mountain quietly loses its balance. Let us know in the comments where you are watching from today. Subscribe to stay informed on real-time Earth science updates as new telemetry arrives.